on Monday we finished looking at this chart, and this chart told us that depending upon the complexity of an algorithm, okay, linear means that basically the number of operations is proportional to the size of the problem. So if n is 1,000,000, you need to do approximately 1,000,000 operations, one per element. If you have a quadratic complexity, then for each problem element in the problem, you need to do a total of n squared operations. That means that you will do something proportionally or approximately n squared times some number, etc., etc. So we can see the logarithmic one. This one is more operations than elements. This one is about the same. This one is less, and this one is a lot more. And of course, there's lots of things in the middle that we're not going to look at yet, but we will look in the future. Okay, so if you look at this algorithm that we described before, which is called bubble sort, we do this algorithm a little bit differently. So suppose now we have elements are going to be from 1, 2, 3, 4, 5, all the way down to n. Rather than comparing going like this, we're going to compare going down. So what's going to happen if we go down, we compare 1 against 2, switch if necessary. If this one is bigger, you switch. If this one is bigger, leave it alone. Go to elements 2 and 3. Switch if necessary, 3 and 4, etc. So after one pass, the biggest element will go to the bottom. Second pass, second element, etc. So the code to do this is the code right here. The red loop is the outer loop that counts the number of passes. And the purple loop in here is the inner loop, and that actually is allowing us to index the actual elements. Notice that j, if xj is bigger than xj plus 1, then we do the swap. Put the j into temporary, put j plus 1 into j, and put temp into the j plus 1. That's the swap. So if the condition is true, you're going to do 1, 2, 3 operations. So if this is true, you're going to do 1, the test, then you're going to do 3 more. It's a total of 4 operations. So what I've done is I've basically labeled the statements here. Statement number 1. Statement number 1, we execute a total of n times. That means we execute it, we run it a total of n times. So the loop says that I should go from 1 to n minus 1. So when I is equal to 1, we do this. When it's equal to 2, we go again. 3, 4, 5, 6, 7, 8, 9, all the way to n minus 1. If it's n minus 1, we do it. But then we have to allow I go to n, and the test is going to be false. So we do n. So n minus 1 times it's true, and 1 times it's false, total of n times. Everybody understand why n? Okay, it's pretty straightforward. Okay, so now the next one is the purple loop. The purple loop basically executes also n times, right? So if you look at the purple loop, it's going to be n minus 1 true, 1 false. But we enter into this loop n minus 1 times. So it's going to be n minus 1 times n. Any questions about that? Questions? Okay, so now we're going to look at line number 3. Line number 3 executes every single time we go into the purple loop. So therefore that's going to be n minus 1 times, because we go in n minus 1 and once we don't. So n minus 1. But we go into the purple loop n minus 1 times, so it's going to be n minus 1 entries into the purple and n minus 1 times within the purple. Okay? And then what about statements 4, 5, and 6? Well, 4, 5, and 6 basically are going to execute only if the condition is true. So the question is, how often is a condition going to be true? And so what we decided is the condition is going to be true about n minus 1 times n minus 1 over 2 times, or about half the time. Now let's find out why we came up with half the time. Half the time means that the first time we check it, we're going to get a value which is going to be either true or false. So if we are checking the first time, in fact, all of the conditions could be always false. True rather, so we'd always swap. False, swap, false, swap, 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 swap. Imagine if the biggest element is here. It's always going to be false, 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 false. So that can happen. Now imagine that we do 1 pass, 2 passes, 3 passes, and n minus 2 passes. If we do n minus 1 2 passes, that means the last n over 2 elements are already correctly placed. That means as we start comparing, it could be true or false, but once we get here, it's always going to be
True.
always going to be false. Because it'll never be a problem. They'll always be in order. Because if these elements are okay, once I start crossing over here, fine, 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 fine. So on average, you see what's going to happen is, so the first time, we can have everything being true. Next time, everything but 1 being true. Everything but 2. Halfway through, everything but half. By the time I do the last one, I can only have 1 true. Before that, 2 truths. So if you add up 1 plus 2 plus 3 plus 4 plus 5 all the way up to n minus 1, you divide them by the number of elements, you get approximately n over 2. So for that reason, I'm putting here that this is going to be true approximately n minus 1. So same as this one, except half the time. So since I have these instruction counts for this particular algorithm, what I'm going to do is I'm going to add these together. So I'm going to add all these numbers together. So I'm going to add n, which is here. This is going to be n squared minus n. It's going to be here. This is going to be n squared minus 2n plus 1. It's going to be here. And then I'm going to add, because these are 3 instructions, 3 times that. Does that make sense? When I do this simple algebra and I collect all my terms, I end up having this bracket in here. And that's going to be 7 over 2n squared plus 13n over 2 plus 5 halves. So you can see that our t of n, which is our instruction count, t of n is our instruction count, is equal to some quadratic function. This is a parabola, right? So you can see it's 3.5n squared minus about 6.5n plus 2.5. Now, as n is getting bigger and bigger and bigger, for example, when n is 1,000, then this is going to be 3.5 million. This term right here, minus 6,500. So this linear term is going to be very small compared to this one. And this constant is going to be even smaller. So we can see as n is increasing and increasing, getting bigger and bigger and bigger, the only term that's really significant in this complexity is the highest order term of the polynomial, which is the 3.5n squared. Does that make sense? Okay, so that's the algorithm. T of n is our instruction count. Now, this is going to be the instruction count no matter what, because basically, in order to make sure that our data is sorted, we have to do the first pass, the second pass, third pass, and then finally the n minus first pass. We have to do all the passes to make sure the data is sorted. If we don't do all the passes, the data may be sorted, but it might not be sorted. So that means the instruction count will be this much exactly for any size problem, whether the data is almost sorted, or reverse sorted. Okay, so that's fine. Now the question is, what if we were to modify this algorithm slightly? So we're going to modify the algorithm. Instead of j going from 1 to n minus 1, as it was here, j goes from 1 to n minus 1, we're going to have j go from 1 to n minus I. N minus I. Let's find out what's happening at n minus I. So if we do n minus I here, that means when I is equal to 1, it's 1 to n minus 1. But when I goes to 2, it's going to be 1 to n minus 2. So what's going to happen is, the first time I compare n minus 1 elements, because the last one is going to be n minus 1 to n, but when I goes to 1, it's going to be n minus 2 to n minus 1. I don't do the last one. Why not? I don't need to do the last one. So the third time, I don't do the last 2. Don't need to. And if I'm doing the very last pass, I will do one comparison, and I don't need to do anything else because I don't need to. So what I've done is I've made this algorithm, we're going to say, a little bit faster. The instruction count is going to be lower if I run this one, because I won't be testing things that are always going to be false. Because in the beginning, let's face it, When I do the first one, it could be all could be true, 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 true. But if I'm already halfway done, it's going to be true, false, true, false, true, false, true, false, true, false, 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 false. Can never be. So therefore, I'm kind of wasting time with these instructions. So I'm going to try to avoid these extra instructions by doing n minus I. So therefore, let's see what happens to our instruction count, which means this stuff in here. You can see that if we change this to n minus I, then it's not going to affect the red line. The red line is still going to be n times. Correct? Yes. The red line is going to be still the same. Now what about the purple loop? Well, the purple loop is going to change a little bit maybe, right? Is it going to change? So basically, are we going to change the purple loop? We'll still enter into the purple loop n minus 1 times. But the first time we execute the purple loop, we'll execute for j goes from 1 to n minus 1. From j goes from 1 to n minus 1. How many iterations is that? N minus 1, which is this, right? So n minus 1, but we have to do one more for the loop to be false, so therefore the total number of iterations will be n. Can you see it here? So the total number of iterations is going to be n. Now the second time we enter into the purple loop, the value of I is going to be what? I is going to be what? 2. So it's going to be, j goes from 1 to n minus 2. So we'll execute for 1, 2, n minus 2. That's a total of n minus 2 true values, and one more to come out of the loop when it's false. So therefore, we'll only execute the purple loop n minus 1 times. When I goes to 3, it's going to be n minus 3. We're going to execute from 1 to n minus 3, which is going to be n minus 3 plus 1 n minus 2. So you can see the number of iterations of the purple loop is decreasing by 1. The question is, what is the minimum value? The minimum value occurs when I goes to its maximum value of what? The biggest value of I for which the loop enters into the purple is n minus 1. So when I is n minus 1, j goes from 1 to n minus n minus 1. What's n minus 1? 1 to 1. So the loop will finally go from 1 to 1, which means we're going to compare, well, j is going to be 1, we're going to compare 1 against 2. That's it. We're done, because everything else is done below me. So therefore, that's going to be 1 true iteration and 1 to come out of the loop. So that means it's going to go all the way down to
1.
All the way down to 2. Because we'll do 1 true iteration and once to get out of the loop. So what we need to do is, in order to find out how many times this loop is going to execute, the purple loop is going to execute, we can't just multiply simply n minus 1 times n. That's not true anymore. We're going to be a little bit more efficient. What we're going to do is we're going to have to add these numbers up together. And so what we need to do is we need to say how much is 1 plus... So basically, we're missing 1. 1 is not in the equation. But let's just do it anyway. So... let's add all the numbers, including 1. So it's going to be 1 plus 2 plus 3, dot, 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 plus n minus 2 plus n minus 1 plus n. So we're going to add all these numbers together. How much is 1 plus n? How much is 2 plus n minus 1? How much is 3 plus n plus 2? N minus 2. Always n plus 1. So what we have is we have n plus 1 is each pair. That's the pair value. The one element plus another element will be n plus 1. N plus 1, n plus 1, n plus 1, n plus 1. But the number of pairs is going to be half of the number of elements. So we're going to really get n plus 1, which is the value, but the number of pairs is going to be n over 2. So we can write it as n times n plus 1 over 2, which is going to be n squared plus n over 2. So that is a different count, and it should be a lower count, okay, of instructions. Now, once we have that, then how many times is this going to execute? Well, basically, how many times does this execute in the first case? When I is equal to 1, j is equal to 1, n minus 1. So how many times does this statement execute?
N minus 1. N
minus 1 times. N minus 1 times. So this executes n minus 1 times. And the second time? N minus 2 times. How about the very last time? How many times does this statement execute? 1 time. So what we need to do is we need to add the numbers 1, 2, 2 to 3 to 4. We have some of those numbers. But we already have determined that the summation of terms as I goes from 1 to n of I, means 1 plus 2 plus 3 all the way to n, is equal to n times n plus 1 over 2, correct? So now that's not exactly what we want, because we want to exclude this one, but it's close, right? So this one, we want to add from 1 to n minus 1. If I want to add to 1 to n minus 1, I can understand the fact that since I already have this solution, since I already have the solution of summing the first n integers, what can the value of n be? It could be anything what? Anything, right? If it's 1, you're talking about 1 element. If it's 2, you're talking about 2 elements. If it's a million, you're talking about a million elements. If it's n, you're talking about n elements. So n could be anything. So I'm going to let n equal to n minus 1. If n is n minus 1, then we have the summation as I goes from 1 to n equal to n minus 1. Of I is going to equal to, substitution for n is n minus 1. Substitution for n is n minus 1 plus 1 is n divided by 2. So that value is the sum of those. Get it? Now, so we can compute these things just like that, and I expect you to be able to do that. If you don't, then ask me or ask the GAs how to do it if you get confused. So the idea is that we are now going to get a different instruction count for statement 2. It's going to be, in fact, exactly this, minus 1, which is going to be n squared plus n over 2 minus 2 over 2, which is 1. And when I combine that, I'll get a number, algebraic expressions. Statement number 3 is exactly this, which is n minus 1 times n over 2. Statement number 4, however, we don't have to divide by 2 anymore, because now, since this algorithm will be testing only when the test might be true, we can make a worst case assumption that it's always going to be true. Because we don't actually know how often is it going to be true. Half the time, 10% of the time, 50% of the time. I don't know. Let's make a worst case assumption. So the worst case assumption is going to be always true. So that means that every time we test, it's true. So that means that this statement will execute each time 3 does, 4 go with 3. And of course, if 4 goes, 5 goes with 3, 6 goes with 3. So in fact, statement 3, 4, 5, and 6 always execute together. And we're going to call this instruction count for the worst case. In reality, chances are it's unlikely that every time you take the test, it's going to be true. But that's the safest bet. It means it'll be no worse than that. It's going to be better or no worse than that. And of course, that's what we come up here. So these are the values here that we've come up here. This is the n times n plus 1 over 2 minus 1, which then can be simplified. And then this is n times n minus 1 over 2, which occurs 4 times. Are you with me?
Yes.
Okay. Now you understand that we are consistent, because when we did this analysis with 7/2 or 3.5 n squared polynomial, we also kind of did the worst case analysis. Worst case analysis because we said basically it's going to be true half the time. Well, if it can all of them, one less, one less, one less, one less, when you add up all the possibilities, divide them by all the possibilities, you do get half the time. So this is still sort of a worst case analysis, and so is this. But when you substitute these new values, what happens is our instruction count, T of n, actually simplifies to 2.5 n squared, which is less instruction count than 3.5. So this is better. So when n is 1,000, we're only going to go 2.5 million instructions instead of 3.5 million instructions, and that's about 2/3 of the time. So it's about a 1/3 speed up, right? 33% speed up if you want to think of it that way. So the question is, we changed the instruction count, we improved it. It's possible that we can improve this algorithm further by reducing the instruction count further, but let's analyze this value versus the previous value of 7/2 n squared. The question is, does this version of the algorithm, where we go n minus I instead of n minus 1 on the inner loop, does this version of the algorithm improve complexity? That's the question. Does it improve the complexity of the algorithm? Not much is not a good answer.
We still have to know this. We don't know.
Do you love your wife? Not much. What does that mean? You love her a little bit, you don't love her at all? Goodness. I wasn't thinking about you guys. I know for you guys it's obvious. You love each other. Okay. So the answer actually is?
Yes.
The answer is we did not improve complexity at all. Really? We didn't improve. Because actually, as n gets larger and larger, we're going to have 5 2n squared, or say 2.5 n squared, or 3.5 n squared. The bottom line, we're always going to be increasing as with n, and n is squaring with that increase. So when n is 1,000, it's 1,000,000. When it's 1,000,000, it's 1,000,000,000. 2.5 trillion, 3.5 trillion. Who cares? It's 1,000,000,000,000. So the bottom line is these algorithms are the same complexity, but one's going to run a little quicker in the worst case than the other. It doesn't mean it's a better complexity, but it's going to be quicker. On the same computer, this one will run quicker in the worst case. In the worst case, meaning that they have the same number, let's say, of swaps, true statements on the conditional. Okay, do you understand what I'm talking about? So basically, when we're talking about complexity, we're not talking about instruction count. We're talking about an order of magnitude. We're talking about a characteristic function that describes this particular algebraic expression. And the characteristic function is n squared. Does that make sense? So these algorithms both are running in n squared time. They are both running in the quadratic time. So basically, roughly speaking, we have an approximate instruction count of n squared. In one case, it's 2.5 n squared. In another case, it's 3.5 n squared. But it's always proportional to n squared. Proportional to n squared means what? What does proportional to n squared mean? Some constant times n squared. So whether it's 2.5 or 3.5, it's n squared. Are you a millionaire? Yes, I am. Okay, what does that mean? That means they have a constant times $1 million. Could be 2, could be 3, could be 50. It's all millionaires. Are you a billionaire? No. That means that constant is not that high, so they're not a billionaire. They're not 1,000 times richer than a typical millionaire. But so you understand? I'm trying to give you a feeling of it. Okay, so that's what we're talking about. So now let's see if we can move. We'll do a little bit of analysis idea. So basically, we want to define something known as a characteristic operation. Very, 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 very important. A characteristic operation is an operation for an algorithm that captures what is the most important, the critical piece of the algorithm. And if we go to our bubble sort code, which operation is the characteristic operation? Is it the one that's counting the passes, the red? No. It's important. But actually, the characteristic operation is going to be our comparison. Because the fewer comparisons I have, the better my algorithm behaves. The more comparisons, the worse it behaves. And comparison is the fundamental operation for sorting. Okay? Comparison is a fundamental operation for sorting. So this yellow operation happens to be the characteristic operation. It's a core statement that's performed repeatedly. It's the key to the algorithm's effectiveness and correctness. And we can use it to find the algorithmic time complexity. What it means is, if you capture or if you identify clearly which instruction is the characteristic operation, and only analyze this one, then that instruction alone will give you the complexity of the algorithm. It won't give you the instruction count because you're ignoring a lot of other instructions, but it will give you the complexity of the algorithm. So clearly, if you look at this one, what is the complexity of instruction number 3?
N squared.
It's going to be dominated by n squared. And how about here? Remember, instruction 3 is still the characteristic one. It's going to be still n squared. So therefore, we would say the characteristic operation are both quadratic in complexity. So this just talks about why we reject certain statements as the characteristic operation, or why we want to accept others. So I'll let you read through this. Now, let's make a variation of bubble sort. We're going to make one small change. We're going to keep everything pretty much the same. Notice that we're going to have basically here, we're going to have this variable j is going to go 1 to n minus pass. And pass is going to be 1, so pass is going to be our I variable, if you will. Pass, because basically when we do a pass, we do everything. If pass is true, do it. Pass is true, do it. Again, we do a little bit less each time, but we do it. So pass is going to be a variable. We initialize pass to 1, and we say, assume that we have swapped on the previous pass. While we have swapped on the previous pass, and pass is less than n minus 1, let's do a pass. So say swap is false. Say we haven't swapped now on this pass. And then we're going to go, j is going to go 1 to n minus pass, which is the same as n minus I. And then what we're going to do is we're going to check the same type of thing. If xj is greater than xj plus 1, then we're going to swap. But when we swap, not only do we actually swap the elements, we also set swap equal to true. So suppose we're entering into pass number 5 of a very large array. So that means pass is equal to 5. 5 is less than some large number. Swap is true because we swapped last time on pass number 4. And so therefore we enter pass number 5, we set swap equal to false. And now we're going to compare elements from 1 to n minus pass, and then basically we compare false, 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 false. Let's say we always have false. It means that none of the remaining elements that could be out of order are out of order. So what that means is that we're going to do this whole j-pass, never having a true statement here. That means we never set swap equal to true. And remember, it was initialized before the swapping, before the pass to false. Therefore, when we come out of the inner loop, we test the outer loop, but swap is now equal to? No, it was never set equal to true, initialized to false, so swap is going to be false. So what that means is, it's going to say, well, pass now is going to be equal to what? Actually, I don't see me moving pass. Pass should be the pass
It's
plus
a
plus.
constant number, no, pass.
So
Plus
what?
1.
Yeah, we should have here pass plus plus on the inner loop. So after the inner loop is done, we should do pass plus plus, right? Sorry about that. Boy, I've been looking at this slide for so many years, never saw a problem with it. The bottom line is pass is increasing each time. It should be. It's not in my case, but it should be. So what happens is, if swap is false, that means we initialize it to false before the pass, and we never swapped. That means nothing else is wrong. Which means that since pass is equal now to 6, or it should be equal to 6 at this point before we increment to the outer loop, 6 is less than some big number, true, but swap is false. So what we're going to do is we're going to drop out of the outer loop, and therefore we're going to be done. Why? Because after 5 passes, the 6th pass did no swapping. So therefore, after 5 passes, these 5 elements are correct. And as I check these all the way down to those correct elements, there's no problems there. I'm done. Fine. Now these are fine. So compare this. This is still fine. I'm done. No swapping. So that means I don't need to do a 7th pass, 8th pass, 9th pass, 1000th pass. So what I've done is I make the algorithm faster for this case. So when the algorithm only requires 5 passes, but it has 1,000 elements, it will only do 6 passes. Why 6? Well, 5 are necessary for swapping. That means we're swapping in 5 of them. But the 6th one doesn't swap, so it says, okay, we didn't swap on the 6th, stop the algorithm. So therefore, this algorithm has the potential to be hugely more fast than the algorithms we looked at before, which are basically, right? So for example, suppose the array is already sorted. How many passes will be necessary? No. 1 pass. You have to do pass number 1. Pass number 1 never is true on the comparison error. So therefore, pass number 2 says swap was false, still false, we're done. So if we require no swaps, then it's going to be 1 pass. How about if we don't swap on the first swap? We don't change on the swap number. Pass number 2, we don't swap. So will we do swap number 3, pass number 3, or no?
Yes.
No. So if we don't swap on pass number 2, we will not go into pass number 3. So therefore, how many instructions? What's the proportionality of what we executed in terms of complexity for that case? The answer is 2n. Because each swap is roughly n comparisons. So the first one, we'll call it n minus 1 is roughly n. So we did n minus 1 on the first one. We did some swaps. We did n minus 2 comparisons in the next one, but no swaps. So n minus 1 plus n minus 2 is 2n minus 3, which is 2n. Right? So 2n. So that means we did it in linear time. You see what I'm saying? Now, the question is this algorithm a better algorithm than the second? Now, we know the second version was better than the first version. Is this third version better than the second version? Because it has the potential to really stop way early when the data is sorted early. The other algorithms just keep flipping things around and checking. Even when the condition is false, for the last 8 passes, it's still going to do that last 8 passes, because that's the algorithm. This one checks. So my question to you, is this algorithm have a lower complexity? What do you think? Well, I'm glad you're not answering so bravely, because there is no perfect answer to this question. You could say, yes, it has a lower complexity, because look, you told us if there's only 1 swap necessary, or only the first pass swaps, the second one doesn't, we finish in 2 passes, and that's linear with a constant of 2n. But what if we need all the passes? Then we're still going to have to do all the passes, plus we're going to have to do all of these additional checks, which is another comparison. We're going to have to do all these initializations, which is another comparison, and we have to do all these assignments, which is another assignment. So if we need all of the passes in order to sort this array, then we'll do all the work we did before, plus extra work for checking if we can stop early, with the answer always being no, 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 no. So in the worst case, when we require all of the passes, we will actually do a little more work than in the worst case when we don't even check. So we have 2 things going on here. So in the best case, we say, well, if the data is already sorted, 1 pass and you're done. Okay, so in the best case, it's better. In the worst case, it's slightly worse. So the very smart student will say, well, what about? Huh?
Best case.
We already looked at the best case. And we looked at the worst case. So the smart student will say, well, what about? Average. You know, like they say, this car gets 95 miles per gallon downhill.
Yeah.
Yeah, baby. I only go downhill. I'm an American. Go downhill all the time. It gets 12 miles a gallon up a sharp hill.
Sharp hill.
Sharp hill. What's a sharp hill? Hey, it's my definition, okay? I'm the EPA, okay, I decide. So the smart car buyer says,
How does it work on a flat road?
well, you say, well, sometimes I go downhill. I'm not an American, but I still go downhill. And sometimes I go up a sharp hill. Other times I go on a flat or a little bit, you know. So the question is, how does it perform? On average. Thank you. I have to pay her $5 because I told her. How does it perform on average? On average, so that's a great question. It's a great question. It really doesn't have an answer. How does it perform on average? You've seen those stickers on cars. MPG in the city, MPG on the highway, average MPG. What does it mean, average MPG? First of all, it says MPG on the highway, 30 miles a gallon. What does that mean? I'm going on the highway, I got 27 miles a gallon. She went on the highway, she got 35 miles a gallon. So what does that mean?
Based on your driving speed.
So there are some other things in there they're not telling us.
Yeah.
Downhill on the highway, 47 miles a gallon. So the question is, so the best case is wonderful, but it's not realistic. The worst case is sad, but it may or may not be realistic. But the average case is most important. The average case is most important, but it's also the most difficult to analyze or even to specify. How do you specify? Well, we specify when we do our average miles per gallon, what we do is we always go on a flat highway in 60-degree weather. Well, I live in Connecticut. I'm always driving in 30-degree weather. I'm usually going up a steep hill. So I'm not getting the same performance as you are. Not getting the same performance out of my car as you are in terms of the MPG. So the average case, we can define the average case, but it doesn't mean that it's really an average. Here's an average case. I never get the average case. She never gets the average case. She gets the average case. You're from Sweden or from Holland? He always gets the average case. He gets very flat near the. You know the thing. You've seen the pyramids, right?
Both sides, get inside the pyramid.
You get inside?
Yes.
And they let you out. Okay. Very lucky. Very lucky. Okay, so the bottom line is the average is a very difficult thing to define. So we have to define it somehow. So let me ask you a question. Okay, let me ask you a question. We know that we have. I'd love to know my phones. I don't know what time it is, so. Who's got time? Anybody got a phone here?
It's 2:15.
Is that my phone? Do you have my phone?
Is that regular?
Yeah, bring my phone.
No, that's a remote.
Huh? You know, it's probably under the screen. No.
Is it in your jacket's pocket?
Will you call my phone?
I'm doing. Maybe it's an office.
Can you tell my wife to pick up some eggs? I just figured it out.
It's ringing.
It's ringing. So I think it's in my office. I think I left it in my office.
You want me to check it?
No, just let me know. We start at 1:30, so let me know when it's about 2:30. 2:15 now. So let me know about 2:30, just so I have an idea where I'm going. Okay. I had this great thing I was going to, ask a question. I forgot the question. Yeah, we're talking about average. So.
Define average.
Yeah, we want to define. We could probably ask this guy. You could probably roll the tape back and say. You can watch me on the screen. Okay, get confused. So again, the question is, how do we define average? So I was going to ask you a question. So now I'm back. So the idea is, we know that algorithm version number 1, we did not we did not have any, no, this is not the right one. We did not have any ability to stop earlier if the data was very sorted earlier. And the second one, we were more efficient because we didn't do all the comparisons that might be false, but we also didn't have any ability to stop earlier. So therefore, we could say when we run this algorithm on a bad data or on a good data, it's going to be the same. The instruction count is not going to vary from this one to this one. But we do know that if we run this algorithm, with the pass plus plus someplace in here, then this algorithm is actually going to behave differently for different data. If I generate random data and I run it, I might do, let's say the data is always going to have 1,000 elements. One time I only need 500 passes. Another time I need 800 passes. One time the data is sorted, I need 1 pass. Next time I need 625 passes. The question is, when will the instruction count on average become better, will it, than, let's say, the previous algorithm here? This one right here. So what is it going to take to improve this algorithm? So the question becomes, how do we define the average complexity of this algorithm? We know how to define the worst case and the best case. The worst case is given a data where, let's say, the biggest element is on top, and that will take it all n-1 comparisons, all n-1 passes to get down to the bottom. That's the worst case, really. And of course, there are many other worst cases. But this is just one case, that basically put the biggest element at the top, and then you have all this other, put the other elements wherever you like. There's lots of combinations of things going on here and permutations of things. The best case occurs when the data is already sorted, so we know that. So we know that the complexity is going to be 2n. Instruction count is going to be roughly 2n in the best case, and roughly speaking, probably something on the order of 3 or so n squared in the worst case. We get that, right? But now what we want to do is we want to actually come out with the average complexity of this algorithm. So I want you to tell me, what does that mean? How would you determine the average complexity? Because now think about what I've been doing. I've been saying, configure the elements in this way, because that gives you the worst case. Configure the elements this way, because that will give you the best case. Now tell me, what is the average case?
I would say random data.
Random data. So if I randomize the data, so I take 1,000 elements and I generate, let's say the elements have keys of 1 to 1,000. I randomize them and I put random elements here. So they're all unique, but they have to be sorted. So then I run the algorithm, and out of 1,000 elements, I find out that I have 997 passes. What does that tell you? Does that tell you, or should I say, does that tell you anything? We have randomized data. Can we make an observation? Can we make a statement? Can we say what the complexity is of the average case?
No.
Can we take
Why not? Yeah.
Can we take the best case and plus the worst case and divide by 2?
We could. The question is, does it make any sense? The answer is, sometimes it does, sometimes it doesn't. For example, in some cases, if you take the worst score and the best score and you add them together, divided by 2, you get the middle score. Sometimes you don't. Sometimes you do. So sometimes you find that this is the best case, this is the worst. So let's say this is the best case, this is the worst case, and the average case is right there. We can actually show it mathematically. In other cases, you find that this is the best case is the worst case, and the average case is right here. The average case is actually almost the same as the best case. Or the average case can be as bad as the worst case. So really, that we know that the average case is not going to be any worse than the worst case, any better than the best case, but we just don't know where it's going to be in that continuum of different stuff. And if we create random data, that's not going to be enough. But what if we create another random data, and another random data, and we do this 100,000 times? We created this random data, and record each time the number of passes. You see what I'm saying? And then I draw a histogram. You know what a histogram is? Bars, right? The bars. So I draw a bar chart or a histogram with those numbers of passes. Will that give us a better idea? I think that will give us some better ideas. And we call, what kind of technique is this that we just did? What kind of technique to get the average? This is an experimental technique, right? We run an experiment. Experiment gives us a distribution. We may say, hey, I recognize this distribution. It looks like the exponential distribution. It looks like the normal distribution. Oh, didn't expect it. Okay. It looks like, hyper-exponential. So we have lots of different things that we might be able to observe experimentally. Now what about analytically? What is the average number of passes we need? We know the worst number of passes is n minus 1. The best is 2. What's the average? Well, we might say take 2 plus n minus 1 divided by 2. But who is going to tell you that that's really going to happen? And the fact of the matter is, with this case, it's even not true. It's not true that the average number of passes is the worst plus the best divided by 2. It's just not true. And here's the reason why. Here's what I want you to think about. Let's think about 10 elements, because 1,000 is so many. We like 10.
Fine for me was 9 factorial. Thank you.
So, let's say 10 elements. So, I think everybody will agree that the number of passes we require for bubble sort is going to be connected somehow to the sequence of the elements. Right? If I have 10 elements and they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I do one pass, everything is fine, I'm done. But if I have, let's say if I have 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, then that 1 is going to require the worst case. That's going to be the worst case, correct? So the smallest element at the bottom already is the worst case. Now, so the orders of the elements matter. If the order is already sorted, then it's going to be one pass, we're done. But there may be other ones that require only 2 passes. For example, suppose that after the first pass, we do one pass, we do one swap. But on the second pass, we don't do any swaps. We're done. So the question is, how many different orders require no swaps? And the answer is, in order to get no swaps, the elements have to be in order. So that means there's only one way for the elements to be ordered in order to require the best case. Am I right? Now, the number of elements is 10. If these elements are randomly organized, how many orders of 10 elements are there? How many ways can I order 10 elements? 10 factorial, because I have 10 choices for the first one. 9 times 8, 7, 6, 5, 4, 3, 2, 1. 10 factorial is roughly 3.6 million. There are about 3.6 million orders of 10 elements. That's a lot of orders for just 10 elements. And so, therefore, and here's the key word here, the probability that a random set of 10 elements requires the best case in this bubble sort is 1 over 3.6 million. You will get an A with a probability of 1 in 3.6 million. That means all the students I've taught in my life, and still have yet to teach, one of them will get an A. How do you feel about that? Not so good. It's a good thing it's not true. You see what I'm saying? So not only, so the best case is great. It's just one pass. But the probability of that is 1 over 3.6 million. Now, let's think about something a little bit different. Let's think about the probability of the worst case, because that's another good one to do. The probability of the worst case, and I'm just going to create one simple example of the worst case, is if we're bubbling down, that means the smallest element is here. Because when we bubble down, that smallest element will only go up 1. So let's put the smallest element at the bottom. How many elements are left here in the top 9 spots? 9 elements. Does it matter how those elements are ordered if the smallest element is at the bottom? It doesn't matter how they're ordered. In fact, they could be ordered perfectly, But the smallest element is at the bottom, therefore the number of passes will still be maximum. The question is, how many different orders of 9 elements do we have? And that answer is?
300,000, 62.
300,000 or 360,000?
Yeah,
360,000.
Yeah.
Roughly speaking, which makes a lot of sense, because 10 times 360,000 is 2.6 million. Duh. Okay. So the bottom line is what we're saying is that if I put the smallest element at the bottom, there are 360,000 orders of the top 9 elements. Out of all the 3.6 million elements that exist, orders that exist, 10% of them are occurring when the smallest element is at the bottom. You follow what I'm saying? That means the probability of the worst case is 10%. But the probability of best case is, that's a technical term for very unlikely. 1 over 3.6 million is very unlikely. If you have 1,000 elements, it's 1 over 1,000 factorial. Don't even think about it. With randomness, the probability of that is not going to happen. That's a technical term for it's not going to happen. If you count on it, it's not going to happen. Could it happen? Yes, it could. Could you be the one person out of 3.6 million students that I've had that will get the A? Oh, it could happen. Yeah, it could happen. Don't count on it. Because the probability is not with you. Okay? Don't start buying a house because Lada is worth 750 million and you bought 1 ticket. You bought 1 ticket. Will you win? Probably not. You might win, you might not win. Unfortunately, might or might not evenly weighed. You might not win up here. You might win. Could you win? Oh yeah. That's why we all buy the tickets, because I feel lucky today. Oh good. We're so glad you feel lucky, because we're just kind of taking the money in. Come on, feel lucky a little more. Buy 2 tickets. 2 tickets. You know, 2 tickets is so much. It's twice the probability of 1 ticket. I mean, honestly, who wouldn't buy 2 tickets? Why would you want to double your probability? Why wouldn't you have 2 shots out of 70 million instead of just 1 shot out of 70 million? It's double the probability. Double. So much more likely. Yes, twice as likely. 10 times more likely to buy 10 tickets. You can have 10 chances out of 70 million. 10 out of 70 million is like 1 out of 7 million. 1 out of 7 million is not as good as 1 out of 3.6 million for the A, by the way. So could you win? Yes, absolutely. Does somebody win? Yeah, somebody wins. Just not you. It's never you. And then when it is you, you end up being miserable later because everybody wants your money. You become the bad person. But the bottom line is, what time is it?
49.
Oh. 29 point what now? So what is the average case? And so I think what I'm trying to show you is that this third version of the algorithm is extremely interesting because it does have different instruction counts for different sequences of elements, different orders of elements. We call those orders what? When you change the order of something, we call it a what? Permutation. So, for example, take the elements 1, 2, 3, 4. So I have 1, 2, 3, 4. I'm going to put them into these locations. So the first one, I have 4 choices. I can put 4, 3, 2, or 1. So I have 4 choices. Once I make this one, I have 3 choices. I have 2 choices. Then I'm locked into the last one. So 4 times 3 times 2 times 1 is 24. That 24 is 4 factorial, also known as what? Also known as the number of permutations of 4 elements. So the number of permutations or orders, so for example, 1, 2, 3, 4 is a different permutation than 1, 3, 2, 4. Different permutations than 4, 3, 2, 1. Different permutation than 2, 3, 1, 4. So there are 24 of them, 24 permutations. So the array contents are permutations. At random, we have a permutation. There are, in 10 elements, 3.6 million orders that we can have. One of them requires only 1 pass. So, it's clear that knowing that there is an average case and the average instruction count will be an important measure for us to consider for algorithms. The question is, how do we find the average instruction count? So the question is, what is your feeling? If the best number of passes for 10 elements is 1 and the worst is 9, what do you think will be the average? Take a guess.
Five.
5 is a good guess? You know what would be really, really interesting? For only those students who like to getting very high grades. So not everybody. But take this code, implement it in your language, put it into a loop, and basically each time you sort the data, record the number of times you passed for 10 elements. Sorting an array of 10 elements is really easy. You need to randomize the array, sort it using this algorithm, and return the pass count. Send it to a file. Then randomize the array again, sort it, send it to a file. Do this 1,000 times. Sort your data, graph a histogram. Look at your distribution. I wonder what your distribution will look like. I wonder how many 1s you'll have. I wonder how many 2s you'll have. How many 3s, 4, 5, 6, 7, 8, 9s you'll have. The histogram, right? I wonder what the shape of it will look like. I wonder if your shape will look like somebody else's shape. So if you do that, then you can do it, but do it on paper, do it on a program, and then show it to me offline. I'd like to see what you have, but you have to have at least an Excel graph that has a histogram so it shows. Okay, because that would be interesting. He's expecting about 5. I'm expecting close to 8. Okay, so I'm saying that most of the time you'll go towards the worst case. I could be wrong, but probably not. With a probability certainty of 0 or more, less than 1.0. What is probability? Probability is the likelihood of something, right? What's the highest probability we can have?
1.
Okay, and what's that called? What's that called in English?
True. Always true.
CERT, certainty, or always true. Okay, so probability of 1.0 is certainty. When something has a probability of 100%, it's certain to happen. As you know, very few things in the universe are certain. So certainty of 100% is not oftentimes. Mathematically, it can occur sometimes, yes. What's the probability that a negative number is less than 0? 100%. That's a pretty easy one. What about something that has a probability of 0 probability? What does that mean? Okay, but we don't know what happens when our Earth goes out of orbit. Maybe this Earth is only sun rises in the east only happened for a little bit of time, that several billion years, and after that it's always going to go in the west until it doesn't go at all. I don't know, kind of sad. But the bottom line is, what is the probability of 0? But I'm not asking for an event. I'm just saying, what does it mean when something has the probability of 0?
Never.
It's not going to happen. It's guaranteed not to happen. So there's certainty and not happen. So in reality, most things are someplace in between. So probability cannot exceed 1 and cannot be less than 0. So it has a range of 0.0 to 1.0, inclusive. Okay? So when I search an array, what is the probability that I will find the element I'm searching for? The answer is, well, I don't know. I'm going to call it P. So if P is the probability that I find the element, what's the probability I don't find the element? 1 minus P. You can call it Q, but it's going to be 1 minus P. Because 1 minus P, and what is the sum of 1 minus P plus P? 1. So it's always certain that something will happen or not happen. That's certainty. Right? Something will happen or not happen. That's certain. You will get an A or you will not get an A in this class. You will get a D or not get a D in this class. You will get a B plus or not get a B plus. That's certain. This class will end now or it will not end now. That's certain. So that's not a very good certainty because you're saying you're covering everything. Okay, so what we're going to look at here is, and I know we probably have about 5 minutes or so left. Oh, nice. Okay. So what we have here is we're going to look at these three types of complexity. So we talked a little bit about best case, worst case, and average case. And I want to formalize this so that we understand what's going on. So I want you to keep in the back of your mind what we talked about in terms of the permutations of the elements in the array. We can have 10 elements in an array, but we know there are 3.6 million permutations, right? What that means is there are 3.6 million orders of the elements. But we also know that each of those orders, if we take all 3.6 million of those orders, each of them in a 10-element array can be mapped to a number between 1 and 9, where that represents the number of required passes to sort the array, correct? Then clearly, if we connect all of the permutations to the number of passes they require, the ones that have the most connections are the most likely to happen. Yes? So, it's clear that out of those 3.6 million permutations or orders of elements, only 9 different things can result from any of them. And that's 1 pass, 2 passes, all the way up to 9 passes. From 3.6 million permutations, they will all map to 9 cases. 1 swap, 2 swaps, 3 swaps, all the way up to 9 swaps. They will all map to 9 cases. So in a sense, if I have 2 completely different permutations, but they both map to a 7, it means that they both will force the same complexity or same instruction count. Correct? So therefore, in that case, we call that a class. A class. So, or an instance. So we're going to say algorithm P accepts k different instances of size n. Assume that n is 10. So if we have k different instances, we're talking about k different instances. So in the case of bubble sort where n is 10, k is equal to? K is equal to what? K is equal to what in this case? 9. When n is 10, k is 9. When n is 100, k is 99. You get the idea? So even though 10 factorial is 3.6 million, all those permutations map to 9 cases, 9 instances. Do you agree that instance 1, which is the number of all the permutations that require 1 pass, and instance 2, all the permutations that require 2 passes, and instance 7, all the instances that require 7 passes. Do you agree that all those different instances are likely to have different probabilities? Or do you think they all have the same probability? We already know that the probability of 1 pass is only 1 out of n factorial. And we know that the probability of n minus 1 passes is what? Well, we calculated it, but what the heck is it generally? Imagine that you have n elements in an array. N elements. Could be any number. Big number. And we're bubbling down. If the smallest element is on the bottom, then how many elements are on top? And how many orders of those elements can we have? How many permutations?
N minus 1 factorial.
So n minus 1 factorial. Okay. How many permutations do we have total?
N factorial.
N factorial. So what's n minus 1 factorial over n factorial? 1 over n. What's 1 over 10? 1/10. So that means that 10% in an element of 10 will require the worst case. What about if I have 100 elements? What percent of permutations will require worst case?
1/100.
1%. 1%. Actually seems like it's decreasing. That's a false confidence. The bottom line is the probability that any of these cases or instances happen, the instance with 7 out of 10 or 8 out of 10 or 6 out of 10, they all have different probabilities. So we need to know how likely is it going to happen. There are two things that are going to be very important. So the best case complexity, so again, I is in the range of 1 to k, where k are all the instances. So remember, with 10 elements, we only have 9 instances, because all of them will be mapped to 9, all 3.6 million. So take a look at all of the instances, all the 9 instances, and find me T of n, where n is 10 or whatever it is, T of n, which is going to be our instruction count of the ith one. So if you give me the minimum for every I with n equal to 10, I is going to be 1 through 9. Give me the one that's minimum, and the minimum is going to be the best case analysis. That's going to be the best case. The worst case is give me the maximum instruction count of the ith instance of all the possible instances. So again, when we have 10 numbers, then I goes from 1 to 9. When we have 100 numbers, then I goes from 1 to 99 for bubble sort. Not for every algorithm, for bubble sort. Let's stick to something we know right now. So best case is the minimum amount of work. The worst case is the maximum amount of work across all of the instances of that size. But that's easy and not always useful. The most important one, the one we'll spend the most time on in this class, is the average complexity of an algorithm given a problem of size n. That is going to be the sum of the products of the complexity of the instance times the likelihood or probability that that instant occurs. So an is across all the instances, multiply each probability by its time complexity or instruction count, if you will. So pi times ti of n. So how many summation, so for bubble sort with n equal to 10, we will have how many terms here? 9, and 9 will be, so we'll have p1 t1 plus p2 t2 plus p3 t3, etc., all the way down to p9 times t9. Okay, do you understand, right? So that's the average case. Now that's the general description of the average case. The most difficult thing is going to be to find which of these two factors. What do you think will be the more difficult, pi or ti? The more difficult one is going to be finding the probability. How likely is it going to happen? Okay, so that's going to be the most difficult. If you think about it, it's a very hard thing to do, even with bubble sort with 10 elements. It's very hard. We know that the worst case occurs when the smallest element is at the bottom, right? And then we can have every 9 factorial on top of permutations. But what about the second worst case? Second worst case can occur when the smallest element is not at the bottom, but one higher. But it can also occur when the second smallest element is at the bottom. And it can also occur when they're both there, or when not they're both there. So now we're looking at very complicated counting of how many instances are going to, how many permutations are going to lead to the same thing. It gets very, 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 very complicated counting problem. So it's easier to do it by experimentation, as I suggested. If you run this program and you run it for 1,000 times, sort 10 elements and see how many times you get 1, 2, 3, 4, 5, 6, 7, 8, 9, then graph a histogram of that. You can say, wow, that's cool. I am really fascinated by this. I'm going to create an array of 100 elements, and I'm going to do it 1,000 times, and I'm going to look at the numbers 1 through 99, and I'm going to graph them, and to see if the shape looks different or the same. Is it a similar shape? Am I seeing a pattern? That's when you start thinking about algorithms and their average behavior. Okay.
Start.
we're going to stop right now. And I'll see you guys on Monday. So have a pleasant rest of the week. Try to eat well and sleep well and work hard.